So Jim, you're here now, and I guess we're
Yes,
ready to
hello.
huh?
Hello, sorry I was late.
Okay, that's okay. We found out things to talk about.
Okay,
Okay.
should I start?
Um, okay, I'll start off here with good morning. My name is Harry Ricker, and this is the Cosmology discussion group for November 2, 2025. And Jim Keene is going to talk to us and give us a discussion about priority in science. Apparently, there's somebody who is got a theory that's very much like Jim's. Is that correct, Jim? I'll let you go ahead and start now.
Okay, is Jacob Barandes copycatting binary mechanics content. There's our title. Description. Dr. Barandes at Harvard is competent in quantum mechanics theory, a delightful personality, and outstanding teacher. However, his new formulation of a theory based on quote unquote indivisibles in talks and papers might copycat key elements in binary mechanics without citing the binary mechanics author and publications. We'll go through some details on that. First, let's just put up for the record a definition from the dictionary that I found of what a copycat is. A person that copies, imitates, mimics, or follows the lead of another. And now we can ask the question today, does evidence support that I'll present below a copycatting hypothesis in this case? Let's start with some relevant information in Table 1 about Barandes and Keene. Barandes is said to be at Harvard. He's a senior preceptor in physics. In other words, he's a teacher there, associated faculty in philosophy. So he's not actually a regular Harvard faculty member, which would be an assistant professor, associate professor, or full professor. Keene is retired from his academic positions and is now at the Binary Mechanics Lab as its director. I've previously been full and tenured professors in universities. We both have a website shown here. Jacob's website is shown, and then Keene has a website as well. Here's the email addresses and the contact point in the XCOM or Twitter space. Jacob Barandes and BinMech Lab. Table 2. Before we get into the meat of the actual content, the physics itself, let's look at some other things which will be relevant down below. The Barandes and Keene appear in dozens of videos. He has quote unquote selected talks listed on his website and numerous interviews, and this is how I found out about this situation, on YouTube channels of Sean Carroll, Kurt J. Mungal, and Toe with Current, etc. And as far as me, again, dozens of videos, talks on YouTube channels of Roger Anderton, John Campbell, and Duke Nucleon is, of course, my channel on YouTube, and also videos on BitChute and rumble.com.
Now, let me interrupt you here.
Sure.
This Kurt Jaimunga video channel is kind of interesting. He interviews a lot of top scientists and philosophy people. So if you're interested in that, that's a pretty interesting YouTube channel.
Agreed. Yes, indeed. Thanks, Harry. Now, warning. In this video, which the link is listed here, featuring Jacob Barandes, oops, that's misspelled, Alyssa Ney, and Roger Penrose, philosophers of science may talk in strange ways as when Alyssa speaks of something that's not nothing. Parts
I
of the
think I've seen this video, by the way. Go on.
yeah. Now, when the philosophers of physics have to be talking about with phrases like something that's not nothing, it's sort of as if they have some blank airspace to fill with such a phrase, and perhaps they really don't have that much to say. I don't know, but I thought I'd just throw that out as a warning. Parts of the second half of this video here, this was the one I watched to, which is the origin of the presentation today, and others may be seen as a tutorial on binary mechanics under another name. Okay, now as a reminder, I'll be using some terms which the group here has seen before, but just as a reminder of what the binary mechanics machinery is, we talk about the spot unit, the spot, and the spot cube, and I've shown this illustration and talked about it before. Okay, let's get into the meat. Table 3, where Barandes and may rename or echo terms and ideas in papers by Keene without citing binary mechanics publications. Item 1. In general, you'll see on the left-hand column of our table, I have various quotes from the esteemed Dr. Barandes. And then I have on the right the binary mechanics content. He talks about a new formulation, new approach to quantum mechanics. I talk about pretty much the same idea, calling it updating quantum mechanics, or comparing full complete quantum mechanics, in other words, binary mechanics, versus the old outdated partial incomplete quantum mechanics. He talks about indivisible mechanics. He even references where he got the term indivisible. Okay, I talk about and call it binary mechanics. By the way, in one of his papers, he's very scholarly to some extent, you might say. In one of his papers, I find about 330 references. And that's, but not a single mention of a binary mechanics publication. New kinds of laws he talks about. And on the binary mechanics side, we reject continuous space and time. As far as Barandes is concerned, I think he still is in the continuous space and time camp, so that would be a difference. And the laws are the new kind of laws that he's trying to describe. In binary mechanics, they're called the based upon the full quantization postulates, quote unquote. Okay, he assumes discrete time. In binary mechanics, this is a very specific item now. We're getting from the more abstract things up here at the top into more specific things. Assume discrete time. And of course, that is the time quantization postulate in binary mechanics. So when I talk about full quantization postulates, plural, time quantization is one of them, the other two being the space quantization and energy quantization. He talks about a configuration in the singular or in plurals, and that would be the system state defined by equations 1 to 6 in binary mechanics. More specifically, a configuration space is similar to the wave function in old time binary quantum mechanics, excuse me, and we have the wave function there as the configuration space. But in binary mechanics, the configuration space is the bit function, which is specifically defined in equation 2. And he talks about a menu of possible configurations. Well, that is simply, it seems to me anyway, possibly referring to all possible bit functions in equation 2. If, let's go back to our figure. The bit function for a spot is just simply these 6 quantities in the 1 or the 0 state. There's 2 in each spot unit. There's 2 and then 4 and now 6. We have 3 spot units in a spot, and sort of filling the 3 dimensions of space, if you will. And so that is the configuration space. Depending upon the pattern of 1s or 0s at these locations, and there's 48 of them, just simply 8 times 6 in the spot cube, that is our configuration space. Okay, to make the mathematics less abstract with an illustration. So the menu of possible configurations, as I mentioned, is all possible bit functions. As I said, there's 48 possible ones in the spot cube. Every system, quote unquote, is in one of its configurations at every moment. Now, this is really an exact, not even a vague, an exact equivalent statement to saying what is the bit function at a specific time. And that again is equation 2. I often talk in my papers about the initial conditions that are set up, and sometimes they're just randomly set up in terms of a particular energy density in the simulated space. And he also talks about initial conditions. This is an important part of understanding what a starting point might be in a possible configuration of your configuration space. Okay, again, you may or may not, I don't know, that's why I'm giving this talk, to see how you all think about this. Think that this is simply a renaming of what binary mechanics is talking about. Okay, division, then he talks again, referring, I think, to quantized times, or specific ones, calling them division events or division moments. He talks in quote unquote about time evolution is modeled in discrete steps, 0t, t2, 2t, and 3t, and the next earlier time. In other words, there are specific quantized times in binary mechanics, as he appears to be describing. Any pair of these times, like say t and 2t, so here n would be 1, and 1 plus 1 would be 2t. Any pair of these times in sequence reduces to 0 or t, you know, the initial state and then the state after one clock tick of or after one time interval t, as seen in binary mechanics papers and presentations and videos. Equations 7 through 17 define time evolution in binary mechanics. He talks about indivisible laws. Well, these would correspond to binary mechanics equations 7 through 17, describing time evolution. An indivisible process, well, binary mechanics time development or time evolution is described specifically as indivisible processes in equations 7, 8, 11, 13, 15, and 17. And in, for example, the paper Binary Mechanics Postulates, quote unquote. Causally local, he talks about this, or causal locality or local causality.
Causally local, yes.
Yeah, causal, yeah, different. I think he uses all permutations of this phrase. Causally local, thanks Ian. Causal locality as well as local causality. Okay, all of those, he uses about any permutation of those two words as possible. And of course, that's the potential in binary mechanics, that's very specifically occurs. In the force equations, 11, 13, and 15, the potential locus, in other words, the size L, where L is one of the primary constants in binary mechanics, the size L cube or locus that holds the potential for a force is always adjacent to the affected locus. And so this local causality is intrinsic to these equations of binary mechanics. All right. Well, we got through that table. That was a long table. I think there was over a dozen rows there. Okay.
I have to admit, Jim, that
yes.
I don't know if you want comments on this, but I found it kind of peculiarly, I don't really understand a lot of these words that he's using and that you're using. So that'd be my comment.
Okay, well, that's may fit into the discussion of whether or not there's copycatting going on and what he and I are actually talking about. So thanks, Harry.
Yeah.
All right, we got 10 minutes.
Yeah, I've come across configuration space before in like classical mechanics. So that, I don't know the other one.
That's what I was thinking too, but I wasn't really sure what. Anyway, proceed, Jim. We got 10 minutes.
Okay, I should be able to finish by that time, I hope. Okay, this rather extensive list of seemingly echoed or renamed theory components is both extraordinary, mysterious, and even suspicious without citing binary mechanics publications or their author. Considering Keene's website, XCOM account, and video appearances shown in Table 2, multiple records at multiple locations exist, which might document if and when Barandes might have accessed Keene's content pertinent to the present presentation. In sum, Barandes cites every conceivable author except the one who published ideas he describes. Sometimes in Table 4, let's look at the fact that also it seems Barandes and Keene use the same terminology, probably with different meaning or interpretation. And that's just another category of events here in this picture. For example, he talks about a single quantum bit, where the table here lists equals question mark. It's not a critique of Barandes' presentations. It's just indicating in particular, I'm not exactly sure what he means by the usage of these terms and phrases. But we do find a single quantum bit, and for what it's worth, the state of a bit locus in the bit function, and that's in equations 1, which describe the spot unit in binary mechanics. He talks about quanta. In binary mechanics, that has a very specific definition and usage, that it's a bit locus in a one state. And then just as a word that's shorter to say than all of that, I use the term quanta in that context in my publications. He talks about integer values, and of course, in binary mechanics, those are allowed spatial and temporal coordinate values, which is why we have to have binary logic form equations for temporal or time evolution, because differential equations, since there are not continuously changing values, where you would represent the value with a real number as opposed to an integer in binary mechanics, you have to have these binary logic equations as opposed to ordinary differential equations, such as what one might use in Newtonian mechanics, integer values. And then he talks about quantized fields. In binary mechanics, that's just bit loci in the one state, or quanta, as I said above, represent two types of energy. And bit loci in the zero state represent the neutrino field in binary mechanics. Finally, quantum mechanics, complex amplitude and its role in obtaining a probability. That occurs, of course, in traditional conventional quantum mechanics. The quantum mechanics complex amplitude defines two types of energy in equations 1 in binary mechanics, as I showed in the figure above. Finally, some differences between the Barandes and Keene approaches. So that there's not all necessary items which suggest possible copycatting, or in table 4, some similarities in how the terminology might be used. We can look at some differences too, in all fairness. He focuses on what people think. It depends upon your perspective, he says, so that as many philosophers in physics do, they'll shift the attention from what's actually happening in the physical world to what's going on in their head. Or they'll say, well, what I compute on my computer, that's the value I get. They don't even want to talk about how that actually occurs physically in what is happening in the real world, on how the real world works. So that's a sort of a difference that one might zoom in on sometimes. He calls his work indivisible stochastic processes. Here the term stochastic is said to mean random processes, as if randomness is a physically existing thing. However, in binary mechanics, it's quite different. Randomness probabilities do not occur, period, in binary mechanics equations. There are no probability distributions at all, which are said to exist. Probability distributions comes from our looking at what exists, our making measurements and observations and analyzing them, and then we can say that there's a certain distribution of this, that, or the other in the data. But of course, in binary mechanics, these probabilities don't actually exist in the real world. And the equations of binary mechanics don't contain any probability distributions whatsoever in any of them. He talks about conditional probabilities. And in contrast, the force equations 11, 13, and 15 in binary mechanics are true-false binary logic statements. And so they're not really equivalent to conditional probabilities as a quantum physicist might think about it. And as I mentioned before, he talks about configuration spaces, plural, but there's really only one defined in binary mechanics, only one configuration space, and that's defined in equations 1 to 6. Okay, he often refers to special and general relativity, quantum mechanics, and the standard model, and he lists 2 axioms in developing his theory. Equations, on the other hand, for Keene's side of the story, equations 1 to 17 are logical consequences of full quantization postulates and observed properties of particles. This latter point here is that I bring in a lot of observed data in laboratories of reputable physicists often at outstanding institutions, internationally known institutions for their physics laboratories and personnel. And that's the observed particles of processes that I'm talking about all the time. He seems to refer more to theories like special and general relativity, quantum mechanics, standard model, and so forth. He says his theory is a work in progress. That's fair and well. On the other hand, in contrast, equations 1 through 17 in binary mechanics are thought to be complete. Whether they are or not, who knows? The future will tell. But at this point, the position of Keene, myself speaking, is that they are thought to be complete. Does indivisible thing have no parts? That's a question one can ask about what Barandes is talking about. And in the Keene column on the right, the spot unit in binary mechanics is seen as a machine with parts. And so actually the term indivisible wouldn't really apply to binary mechanics as it has been presented, because the spot unit spatial object is actually a sort of device or a machine that actually does things. And it does have parts, apparently. Okay, now table 6 is our last table. Harry, should I present this in the second session, or is there how much time do we have left here?
I think we ought to go to the next session because we got less than a minute.
Okay, I'm showing, let's see, what am I showing?
I have 40 minutes and 18 seconds.
Oh, okay. Well, let's go then with the next session. And
Okay.
I'm sorry.
Okay, I goofed up. You want to send me a share request, Jim?
Sure.
All right. Okay, you got cut off there. I think you were going to apologize for being late.
Yeah, thanks, Harry. Okay, so to finish up what we're talking about and open the discussion, because I really am very thankful to present this material today to your esteemed selves, and really am interested in how you might handle this in your own minds. So let's finish up here in our table 6. Barandes says 4 criteria are, quote, required of any good theoretical framework in physics. This is sort of a interesting point that he makes, and I give him credit for that. 1, it has to be empirically adequate. The predictions have to agree with what we're seeing. In other words, empirical data. At the end of the first session, a few moments ago, actually, I talked about how binary mechanics does mention important empirical data as related to the theoretical points in binary mechanics. Barandes' second point is it shouldn't be vague. 3, there should be at least a schematic in principle story. That's a little awkward phrase, but that's just how he put it, and no problem there. A schematic in principle story, or some account or narrative, you might say, to be told about how the classical world is supposed to emerge. 4th, it shouldn't depend on a long list of ad hoc extra empirical axioms. In other words, I think his point 4 is that we shouldn't have to keep adding assumptions as we go along. Everything should flow from the first principal axioms of a theory. He suggests
Jim, let me stop you here. Does he
Sure.
Does he mean point 2, point 3 says there should be at least a schematic in principle story to be told about how the classical world is supposed to emerge, and then that is modified by 4, or is 3 separate from 4?
Let's see. Is 3 separate from 4? I think it sort of is, because I think in point 3, he is stating that from your starting point axioms, you should be able to build a narrative about how our classical world, such as the universe and the cosmology we often talk about on these Sunday sessions, emerges from those particular axioms presented. Whereas
but that emergence doesn't depend on a long list of ad hoc extra empirical axioms.
Yes, so you might say that his third and fourth criteria overlap. Is that what you're saying, Harry? I think you're right.
I'm saying 4 as a modification of 3. So
Oh,
that's
okay, that they do overlap. Okay, yes, good point. Okay, but anyway, this is how he presents 4 criteria, and I can't speak for him to defend that his third point and fourth point are substantively different or sort of related, as Harry has just pointed out. It seems that they are related. Anyway, he suggests that existing theories, here's the punchline, existing theories fail to meet these minimal requirements. But in my humble opinion, he does not mention that binary mechanics does meet these requirements. Okay, Table 6, Barandes' requirements for a good theoretical framework. And of course, he is mentioning these 4 criteria because he wants to reject all the previous theories, but keep his going, the one that he's working on in the indivisible stochastic processes, as he calls it. Now, I reordered points 1 and 2 just for convenience here in Table 6, so that we can look at his criteria that the theory should not be vague. And of course, in binary mechanics, we meet that criteria, I think, because we have specific full quantization axioms. And the system state is defined in equations 1 through 6, and the time evolution in equations 7 through 17, as I've said probably too many times today in this presentation. That's anything but vague. It's very, very specific. Okay, the second criteria, as I've ordered them, is predictions and empirical data agree. In binary mechanics, now remember, Barandes doesn't quote any of this on the right side of the table here in his presentations. In binary mechanics, we have the fundamental constant derivations. Those are for alpha, coupling constant, the speed of light c, elementary charge E, Planck's constant H, and electromagnetic moment. We have the electron zero electric dipole moment and the fractional 1/3 electric charge of the electron as empirical data. We have the proton positive EDM as contrasting the 0 electron EDM, the non-spherical shape of the proton, and 8 elementary particles, all of these related to observations in other labs, as well as work at the binary mechanics lab in terms of the derivations mentioned above. How about point 3 of his criteria? He talks about how the classical world emerges. Well, right here in Harry's wonderful Sunday seminars or sessions, binary mechanics cosmology has been presented. And it builds in a logical, step-by-step way the universe from vacuum particles to astronomical objects. Point 4, no extra ad hoc axioms required. And of course, binary mechanics, as I've said, only postulates and equations 1 through 17 are needed. Now, we're at our finish line here. So binary mechanics, as far as I can see, and you may have a different point of view, and that's why we're here today to discuss all this, binary mechanics checks all 4 boxes above. So that when he says that his work on indivisible stochastic processes and these criteria reject all other theories, in other words, he's saying, I'm the last man standing in my theory, he doesn't even mention binary mechanics, that binary mechanics checks all 4 boxes and can't be rejected according to his own criteria. Thus, at the end of the day, Barandes might be counted as maybe a convincing promoter of binary mechanics at a famous academic institution. He just needs some scholarship, perhaps, to upgrade, a scholarship upgrade to cite relevant sources in binary mechanics publications to maintain integrity as a credible investigator. So there we go. That's thank you. I'm done. That's my little talk for today. And I invite your discussion.
So what does onx.com mean? Does this mean you've posted this on X?
Oh, well, that's just some notes I have down below here. For example, these are the x.com handles that are relevant to today's talk to some extent. And starting here with Sean Carroll. And let's see. Okay. This line here, the middle line, are all places on Twitter, the Twitter handles for places where Jacob Barandes has been giving these talks, which I've been quoting from. And so, as you can see, he's done like an internet blitz of sorts. He's been all over the place on this row here, presenting his new formulation, which fails to cite binary mechanics at all. Here, this is just some notes that are not really part of the talk, but there they are. For example, he says in one talk that Simon Mills and Kevin Modi, according to him, introduced the individual processes concept. Their paper said nothing about what you could do with them, he says, and so he decided to build his new formulation.
That was all very remarkably similar.
Really, you think so?
I think so.
Okay, that's interesting.
I mean, I don't know if he stole Jim's ideas, but I mean, have you thought about writing to him, Jim, or you know, going on Demystify Science, saying, hey, you know, I have almost precisely the same ideas as this guy who was on your show, and you know, I mean, I don't know if you feel like that, but just a thought.
Okay.
What struck me is that there have been many examples in science where you appear to have thinking almost contemporaneous, simultaneous moves to get some new idea. Maybe the calculus, Newton and Leibniz, and maybe a better example would be the theory of evolution by natural selection, Darwin and Wallace. And perhaps one explanation for that is that, you know, knowledge is actually leading in a particular direction and it's being accumulated and it's international, even more so nowadays than it was in the past. And it just takes, you know, some individuals to make the extra leap. And they might make that at, you know, roughly the same time. So Jerry's point is a point I was going to make to you, Jim, as well, because what Darwin did is he desisted from publishing the work that he'd been writing up for many, many years because he wanted more precise evidence. And then suddenly this paper was presented to him for review, which was going to be presented to the Royal Society by Alfred Russel Wallace, a fairly unknown naturalist. And he looked at it, he said, if you had given somebody my work over the last 20 years and asked them to summarize it, they couldn't have done a better job. So what he did is he wrote to Wallace and he made the point, and Wallace was very noble. He said, that's fine, I accept everything you say, and let's make a joint presentation. So interestingly enough, I must confess that I'm not really qualified to see whether there is a very great similarity or not. I have to kick for touch a little there. But I certainly would think that you know, rather than maybe jumping to the conclusion that this guy is a plagiarist and he deliberately got some ideas from binary mechanics and he wanted to hide it and maybe make the claims himself, I think it would be worth Jim's while contacting him humbly and pointing all this out to him.
Well, thank you, Ian, for that sort of approach. I have two comments or reactions. First, once this talk is published on our wonderful Roger Anderton site, I plan to make a Twitter post. Okay, excuse me, XCOM. It's now called X instead of Twitter. This is so confusing, but anyway, it is what it is, right? I plan to make an X.com post citing or linking that video that Roger Anderton presumably will post on this session today. So that, and in that post, we'll put the handle or the XCOM account for Barandes that I mentioned above here. This is his handle on XCOM. And so that the way XCOM works, when you specifically put a handle in a post, that the feed for that person or organization will receive a copy of the post. So it's sort of a way to send an email without sending an email to somebody. Okay, now my second point, and I'm glad that Ian brought this up. I think he was specifically talking about this, that in this particular video here, perhaps I could even copy it into the chat. But anyway, in this video here, Roger Penrose, of course, a Nobel Prize laureate that I think many of you are aware of who he is. And he has done work or said things relevant to cosmology, as I think we know. Says in this particular video something very interesting. He says that he developed an equation to solve a particular problem. I don't recall exactly what the problem was, but it all reduced down, the solution of the problem boiled down to producing a particular equation. He says in this video, in this story, which he tells, that he discovered then that another person had come up with exactly the same equation 2 years earlier. And Penrose, and I think this is to his credit and to his sense of integrity, says that he then acknowledged that another person had come up with exactly the same equation and solution to the particular problem on the table 2 years earlier. And so in that case, Penrose, I think, is a very honest, straightforward player. So that's the second point I'd like to make in response to what Ian was saying.
By the way, Jim, just one thing. That video you're referring to there, is that the same one as you posted when you talked about 10 days ago, or the week before last? Last week, in other words.
What did I talk about last week?
You talked about the same subject, really.
Physics follies. Physics follies.
Physics
follies.
Exactly.
Yeah, in the physics follies. No, it's this video down here. If you can see my marker right here, it's this video that I referred to in the physics follies paper.
Because I had a look at that, admittedly at double speed. I really didn't have the time, but I went through and I just really saw that this chap, Barandes, and another man, another academic, just arguing and maybe showing how their virtuosity and knowing all aspects. I didn't really see very much coming out of it. So maybe the other.
Yes, the other man was Scott, who is a tenured professor at Harvard. Okay.
Yeah. Yes. An older man.
Unlike,
The other fellow's quite young, I think. He looked quite young, Barandes.
yeah, he has a few gray hairs coming in, and it's Scott A. I don't recall his last name. It begins with A, but he's Scott in that video. And that video is a very troublesome video. This is the one I quoted in my Physics Follies presentation and paper that's now published on my website, by the way. And the frustrating thing is a very long video of 2.5 hours, a long time. And both of these individuals seem to have a great deal of trouble expressing themselves in a single coherent sentence without umming and awing around and saying, you know, and and it's a very frustrating video to watch. The only reason that I went on through it, because parts of the second half of this video, as I've stated here, may be seen as a sort of tutorial on binary mechanics under a different name. Now, this group here is so polite and kind. Feel free to tear apart what I presented, because your critical comments are welcome. For example, somebody might say, Jim, you're just being paranoid. Well, could be, but paranoia, we wouldn't be here without a healthy dose of paranoia to survive as a species. You always have to worry about what can go wrong. So unless humans as a species have some degree of paranoia built into our systems, we probably wouldn't even be here today to talk. Somebody else would have wiped us out, another hominid variant perhaps in the distant past. Haha. Anyway, so yes, this is a different video that was featured in the Physics Follies than the one above. The one above, we don't really get into talking about his theory. The host of that video apparently had some other objectives, but it's only an 11-minute video.
Oh.
But I find it very interesting that Roger Penrose thought it appropriate to point out that something that he could have taken credit for, okay, was actually, he discovered afterwards, done by someone 2 years before, and he recognizes that fact and applauds that particular person. So the question is to what extent in today's video and in today's topic has Barandes possibly accessed binary mechanics content and not cited it or recognized it? In the four criteria.
You want my answer to the question, Jim?
Oh, of course, I want everybody's answer.
My answer is no.
No to what exactly?
I don't think he's read any of your work or knows anything about it.
Okay, that's a very viable response to the hypothesis of today's talk.
Okay, so to justify that conclusion, if you want to skip down a bit, I think he's still using the stochastic method, which is, in my mind, the big difference between what you're doing and what he's talking about. He's still he's still talking about probability distributions, and you're not. That's as I understand it, that's a major difference.
I think
exactly.
I think it looked as if like Jim had, you know, his words, you know, it looked like very similar concepts or the same concept expressed in different words. Some of it,
except for the probability distribution part.
Yes, and also I must say, unlike my views as expressed in the Physics Follies talk and paper, which is now published, Barandes refers to, this is in support of Harry's take on all of this. That but Barandes in all of these talks talks a lot about special and general relativity as if they're correct theories, quantum mechanics as if it has a whole lot of merit, and the standard model. And by the way, I hope I'm not changing the topic here, but I've noticed, at least in my YouTube feed, that a whole lot of famous physicists, by famous, I just mean people generally know their name, they're Nobel laureates or well-known physicists for their publications and so forth. A whole lot of videos are suddenly appearing in the last year or so, or in the last months that I've seen on my YouTube feed, questioning quantum mechanics with titles such as "Quantum Mechanics is Wrong," "The Wave Function Does Not Exist," "Hilbert Space Does Not Exist or is Wrong," so forth and so on.
I have seen those too.
May have been prompted by Roger Penrose's apparent U-turn.
Yeah, he says quantum mechanics is wrong, if I'm understanding correctly.
Right.
Exactly, yeah. So now a person made a comment in my Physics Follies talk on the John Chappell channel on a previous Saturday, last Saturday, not the one yesterday, the one prior to that, or 2 Saturdays, I guess, prior to that, oh my gosh, what was I going to say about that? The point left my mind. A early warning of senility. It'll come back.
I think you were saying some comment had been made during that presentation or something.
Yeah. Well, I just find it unusual with regard to this particular point that, and this favors Harry's reaction here, that Barandes frequently refers to these theories, special and general relativity, quantum mechanics, standard model, and so forth, as if they have a lot of merit, or as if they figure into his work, like he's talking about space-time quite a lot and so forth, which is not quoted here because it didn't seem to be relevant. And at it, so he's coming from a different approach. Now, my position is, oh yes, I just remembered the comment that I forgot a moment ago. It was for a guy whose initials are NP. I won't mention the name, but everybody here knows him. And he was saying that in the comments for my presentation on Physics Follies, that it's actually a good thing that ideas that I've been presenting are presented on the internet by others, whether or not they are quoting binary mechanics. He didn't say that specifically, but one can assume that this is a good thing, a good trend. And I would tend to agree with that comment that you made. Excuse me?
Excuse me, I sneezed, excuse me.
That I would tend to agree with that comment, because in a way it's sort of preparing the ground for a wider awareness of the work at Binary Mechanics Lab that I've been doing by others in the physics community. They're sort of being prepared for it, if you will, indirectly, like plowing the ground before you plant the seeds. So that's a thought that is sort of optimistic. I guess I'm the incurable optimist to some extent.
Yes, I was going to comment on that. I think you're right about that. Okay, so essentially, to get to my point again, this is a question. Do you one of the main points when you read about quantum mechanics and they debate it is quantum mechanics is indeterministic, I think that's they characterize quantum mechanics as indeterministic. But your binary mechanics appears to be deterministic. Would that be a correct characterization of a difference?
Yes, I would think so. And in the popular parlance, this fact of a theory that is deterministic, such as the one that, such as binary mechanics, that this disagrees with free will. But let's say that binary mechanics is correct. I'm going to do a demonstration now, right now. No, notice my hand. Although everything in this environment here is, in terms of the physics, is deterministic, I can decide right now to raise my hand and watch what happens. You see that? Or I can decide to lower my hand and watch, and you see what occurs. That's free will. So free will is not at all necessarily inconsistent with a physical theory that is, technically speaking, deterministic. I can also, as alternatives, with my own free will, I just thought of this now, wiggle my fingers. So there's my demo, a real life experiment. Today, you saw it on Harry Richter's Sunday Cosmology.
Okay. Okay. Well, I think you answered my question. Oh, I was going to comment. We had less than 10 minutes. That was the message that came up. Okay. Oh, Roger wants to say something.
Hello, hi everybody. Well, I just put it through AI, ChatGPT, and it recognizes there are similarities and differences between the two theories, and it says it gets to its conclusion.
Which are the two, Raj?
Your theory and Barandes' theory. It recognizes there are similarities, but it gets to its conclusion of saying there seems to be independent development within a common intellectual niche. So it thinks you're both coming at the same sort of thing from independently of each other.
Well, that's almost the point I suggested earlier.
So that's what AI is thinking. And of course, AI can be wrong and it doesn't really think, but that's what it's processed.
Well, I would call, thank you, Roger. I would call that interesting, because here we see that binary mechanics might be edging its way into the consciousness, if you will, of AI.
Yeah.
And go ahead.
Okay. So there's similarities in really, so I would say you need to contact him, but sometimes with these people, they don't want to talk to people they consider dissidents, do they?
Well, and evidently the point that Jim raised a moment ago, that he seemed to be in the other video very congratulatory about relativity theories and quantum theories and so on, and positive about them. Well, what else would you expect from a mainstream academic, I would say?
Yeah, he probably doesn't want to be associated with somebody who's going against those sort of things. He wants to be firmly within the mainstream camp. I think with Roger Penrose, he fully supports relativity, doesn't he? And that's why he doesn't like quantum mechanics. And if you come
I think I talked about that. He's to resolve the conflict. He says quantum mechanics is wrong. I think that's his solution to the conflict.
I have been to talks by Roger Penrose, and he was fully in the relativity camp.
Right.
So attacking relativity as I do, didn't really think it's worth it getting in touch with him. Yeah.
Well, he's very much
as
following
far as
in Einstein's footsteps then,
Yeah.
because that's basically, you know, the Einstein
Yeah, but I
method.
don't think he follows everything Einstein says. He's come up with his own interpretations of it. Because I kind of nitpick with what Einstein says and what people have said later. It's sort of it's not the same thing. They've done ad hoc add-ons, haven't they, to it, and amendments to relativity and all that stuff about the beginning of the universe from a singularity. Hawking's got tied into that with what Penrose was talking about. So they're all in their little club.
well, as far as contacting Jacob Barandes,
Yeah.
I included his email above, so a little screenshot of that in the previous parts of this presentation, and that was in table 1 about the about table. Anyone here is free to, email him about this particular presentation and what his reaction and thoughts are. I intend to do this once the video for today's talk and discussion are up and on the internet, and therefore can be on Roger Anderton's wonderful channel listed. Then I'm going to make some XCOM posts referring to that video with the handles of Barandes and Harvard Physics, and maybe even Hassenfeller, Savina, and and to further the question. And of course, in that video of today's goings on, he will see, if he looks at it, what's that people here think that he just maybe is doing parallel work and not actually copycatting, that the hypothesis of copycatting may not be fully established by what I presented and as represented by the reactions of people here today, which would be fine.
And without teaching one's grandmother to suck eggs, not that you're a grandmother, but I mean, it might be expedient if you couch it in some terms that you basically have that view. Give him every opportunity to be very polite, and come back to you and be generous. If he wants to ignore you or be nasty, let him do that. I wouldn't go in, with all sort of drums banging that you think that there's a probability that he was plagiarizing your work. I might go in very, very gently, and but it's up to you. Obviously, I'm just
well, that's very, very advisable, and even in today's talk, excluding this present discussion of my talk, which I gave earlier in today's session, I present the copycatting as a hypothesis and not as a given charge, because actually, if there was copycatting, and by the way, as I pointed out above, there are multiple records in multiple places that if Barandes and any number of computers which he uses either at home or at work had accessed binary mechanics website, those records exist, okay? And so in a way, Barandes may be a little bit in crisis and perhaps respond in a very favorable way. And I hope that happens, because I have no ill will, as our person commented, as I mentioned before, that it's actually a good thing if people are echoing binary mechanics ideas in the internet media and in papers, because that can't be viewed as a bad thing as far as binary mechanics is concerned in my work. And so that's my reaction there.
And you have acceded to that. And you also acceded earlier on to the possibility, you said yourself, that you may be a little paranoid and that a little paranoia may be useful in science. So you've actually said that yourself.
Right. Well, yes, thank you.
Okay, we're coming up to the end here. We got about a minute. So any quick comments before we end this particular segment? No takers. Okay. Well, thank you. I have some particular questions that maybe we could take up in the next segment.
Wonderful.
But they don't really relate too much to what you're saying. It just kind of relates to my questions about the terminology that he is using as opposed to your terminology.
Wonderful. That's the science of it. And as you indicated in an email to me, you hope that
I'm not an expert. Yeah, I'm not an expert, but I can give you one example from quantum mechanics of people independently coming up with something. And this is with my second thesis advisor, Abner Shimoni, with these correlations with entanglement, polarization entanglement. And I know he, with his graduate student, Michael Horn, they came up with this inequality, the CHSH1, where you have these 4 settings for polarizers. And all the experiments for this, when they all came up in favor of quantum mechanics, that they used this inequality. Well, it turns out the one who actually got the Nobel Prize, John Clauser of Berkeley, he came up with a version of the inequality, and Shimoni and his graduate student independently came up with the same inequality, and then they collaborated on a joint papers, the CHSH one. So this can happen, that 2 people independently come up with quite similar ideas, and then they sometimes may make this known, and sometimes actually work together afterwards. And I suspect that something similar is happening in this case. I could be wrong, but that's my suspicion. So I kind of agree with Harry there.
Because there have been numerous examples of
let's
disputes as to who originated something, who originated wireless communication. You know, Marconi, he was a very good maybe promoter and businessman. I think it was an act of Congress in 1943 which actually laid the claim to Tesla. He said he actually invented wireless communication.
Maybe they did
Same
it
with the motor car.
independently.
Who invented the motor car?
Or the telephone. And again, I think it was independent. Bell and even Edison.
Yeah, and the same with the television.
Okay, I wanted to. All right, go ahead.
No, I finished.
I wanted to ask Jim, what is this issue of entanglement? Does that appear in anything that Barandes is doing, and does that appear in anything that you're doing?
Well, I've noticed that there are a number of papers that show that entanglement can be accounted for with classical ideas. For example, just in a nutshell, suppose that 2 particles with opposite properties emerge, for example, an electron and positron as a result of converging gamma rays, as we often see in a Feynman diagram. And so that at time 0, you might say, in a very local area, you've got 2 particles with opposite properties. Now let's assume that those 2 particles wander off into space and they continue to have their opposite properties. There's nothing particularly mysterious about that.
Except I don't think that always works. That's the like joint cause. But there are experiments. I don't know if I can name them right off the top of my head. But one is one by aspect that seem to go against that. But I mean that's the obvious reply. But there are counterpoints on that one.
Okay, but that might be something interesting to look at. I got from your summary that Barandes doesn't say anything about entanglement.
Well, I've watched a number of videos that he's produced or that have featured talks by him, and I don't recall any specific mention of entanglement. Can't say that it's not there, but
Okay.
yeah.
So we don't know whether that's an issue or not. Okay, well.
Well, it could be clarified in a possible communication to him.
Mm-hmm.
Well, I just brought that up because I noticed that wasn't mentioned in Jim's comparison. And that's been an issue in quantum mechanics that's really been a hot topic for the last few years.
Yeah.
Well, more than the last few years, I guess.
Well,
Yeah.
when Roger posts the video for today's session, I plan to contact Barandes in my own way, as it were, indirectly through XCOM, one or more XCOM posts referring to the video, and also tagging the account names of Jacob Barandes and Harvard Physics and so forth, so that he will receive this information and perhaps watch the video that is being produced right now.
Okay.
And, uh-huh.
Could you put your presentation back up?
Oh, okay. Let's see. Share. Send request. Let's see. Share. Let's go with this one. And there it is, I hope. Now I don't get to, since my shared screen takes up most of my screen.
Oh, there we go.
To see you guys.
Okay.
I like to see you guys, but I can't see you. But anyway, there it is, Harry.
Okay, let's move up some more to the top. My comments have to do with this. Okay, you passed part of it, but anyway, this terminology of indivisible. Go back up. He doesn't seem to be using the term quantum. He seems to use the word indivisible.
Yeah, he in my understanding, which may not be fully correct, because again, you have to let Barandes speak for himself, as it were, rather than try to speak for him. But so this is just my understanding, is that he wants to distinguish his new formulation as being something that is different from and replaces quantum mechanics. In other words, he has a very big aspiration there, you might say.
Okay, so that means he's inventing a new kind of terminology, indivisible mechanics, he's calling it. Apparently,
yeah.
What you're saying.
And I left out the term stochastic.
Yeah, and I forget exactly what that means, although I'm an electrical engineer and ought to.
Well, it's
Random.
apparently just a synonym for random. So he doesn't give up the idea in his axioms that that randomness is somehow an inherent property of the way the universe works.
I think stochastic refers to randomness in time. If I'm
Okay.
not.
Oh, okay. Yes.
All right. Okay, so something is indivisible. And this is kind of where the issue is. In your case, in binary mechanics, pretty much everything is quantized, correct?
Well, I guess you could say that.
Well,
However,
you have full quantization.
the spot unit, though, is not necessarily an indivisible object. This is some sort of a device or machine which has to implement the equations, the time development equations, particularly of binary mechanics. So you have to look at this as a machine of some sort. And it therefore, and I have a paper on the components of the spot unit. Like, for example, some of the walls have to be barriers which energy quanta cannot move through. Some of the walls have to be valves, which means that an energy quanta can only move in one direction through that wall, and so forth. In other words, that the spot unit does have parts, so that applying the word indivisible to binary mechanics is not fully correct in my view, because even the quantized length, time, and energy units postulated by binary mechanics in full quantization, that's what full quantization refers to, do not imply or lead to the conclusion that that this particular machine here, the spot unit, is indivisible. That there are not that it is not made up of parts. It must
I
have
see what
certain
you're
parts.
saying. Okay, but I think he means if you go down to I think he means that time is not, that there's quantized units of time and quantized units of space. I think that's what he means.
Yeah, and if that's the case, and recognizing that he himself states that his theory is a work in progress, but nonetheless, as far as I can see, he doesn't give the value for a discrete unit of time or time interval or a spatial interval either. In other words, those values are what I call the Keene scale, or I call them also the primary constants of binary mechanics, those three values for time, energy, and space or length. So as far as I can see, thus far, Jacob has not proposed any particular values for this discrete time or configuration space dimensions in terms of their size, what lengths might be involved, and so forth.
Okay, that's interesting.
I take it
In
you
other
do,
words,
Jim, wouldn't you?
he's way behind binary mechanics. I mean, he's so far behind on the racetrack that you sort of have to have your binoculars if you're in the crowd to even see him trying to come around the last bend in the racetrack, whereas at the time, binary mechanics is already crossing the finish line, if you want an image there.
Go ahead, Bob.
Yeah, I take it that you actually do give sizes for these, Jim. I think you went into this at one of your talks, but maybe you can remind me what they were.
Right. Okay. The particular values are known as are called in my publications the primary constants, and those three values for length, time, and energy are stated there. I won't try to quote them right now off the top of my
How about
head.
rough order of magnitude, maybe?
Okay, yes. Okay, the rough order of magnitude is for energy, it's basically 1/3 of the electron rest mass. Okay. And for time, it's going to be about in the vicinity of 10 to the minus 25 seconds.
That's
And
very
for
short,
length,
yeah.
it's about 1 femtometer, or actually 2/3 of a femtometer. Now, that's based
roughly
upon,
the sort of the new size of a nucleon. roughly. Yeah.
Yeah, you're right on target, Robert.
And your 1/3, that sounds like quark theory.
Yes.
Well, actually, the length measurement came from scattering data done way back in the 20th century.
Like Rutherford for the scattering on the nucleons, but
And they got a value of about 1.2 or 1.3 femtometers as the proton radius, using a simple Newtonian mechanics billiard ball type of analysis. What would be the size of these balls if the observed scattering spectrum, or the spectrum of scattering angles, is obtained. And you notice that what I then did, I said, okay, a 1.2 or 1.3 femtometers as a proton radius according to empirical data. Gee whiz, that's sort of like two primary constant lengths in binary mechanics. And so that if we half that, then we get to the 2/3 femtometer value for the length constant. In other words, that would be the size of this cube. And there are two of them in the spot unit. That's our, in italics, L is our length constant.
you know, I even saw in your diagram you mentioned quarks there, so it does sound like some version of a quark theory.
Right. Well, actually, binary mechanics, as far as I know, is the first in table 1 of the first binary mechanics paper in 2010. This table 1 is also repeated in a more recent paper called Binary Mechanics Postulates, that I was the first to propose that the electron consists of 3 parts. And so that then we get the idea of fractional electric charge, and which now has been observed in the Hall effect, in the so-called anomalous Hall effect, where units of current, which are about 1/3 of that which would be expected if the charge of the electron were the elementary charge value and it was indivisible, but they were observing amounts of current which would correspond to about 1/3 of electron elementary charge E. And so in our basic constant, secondary, what I call the fundamental or secondary constants spectrum there. So, so just rather recently, and this was published by Long Ju's group at MIT, that's LONG space JU, in Nature. And they claim, and other commentators of this paper claim, that this is evidence that electrons actually consist of 1/3 fractional charge elements or components in it. And I was the first, as far as I know, to predict this in the table 1, which I mentioned before.
Okay, can we move down to the next page?
Tell me when to stop.
Well, there's a lot of, there's a lot of things here that can, causally local versus causal locality. I mean, that sort of, that kind of could be clarified, I think. I'm not sure what individual, all these terms are sort of unclear to me, and anyway, that would be my comment there. I'm not, in your case, you're removing the vagueness of their terms. So you hit that vagueness requirement pretty hard there. I mean, you're obviously on your side of the table, you're giving specific non-vague answers to what appear to be vague assertions or terminology, if you will.
Yes,
So
I agree.
You hit that pretty good.
For example, if we go back to the spot cube, notice that right next to the let's look at this blue spot unit and the yellow one, which happens to be in the electron, and this happens to be a matter quark particle over here in the dark blue. Now, in terms of local causality, this arrow here, this component of this spot unit can act as a magnetic potential, actually affecting a one state located in the adjacent parallel, what I call concurrent spot unit. And that would then cause the acceleration of a one state here forward within the spot unit to the arrow position. And so that is local causality. They're actually apparently touching, or as far as we know, there's no distance between these two, that the wall of one spot unit, the blue one, and the wall of the yellow one are juxtaposed in some manner that actually we don't know exactly, but it certainly is about as local causality as is possible to imagine within the framework of this binary mechanical model. Causally local causality.
Yeah.
Let's move down to do you have a comment, Bob?
Well, yeah, just with entanglement, that seems to be non-local causality, if you buy into entanglement. And I don't think
what is causing what? Here we might be confusing what we measure with what of why we measure it as two different things. For example, where is the non-local causality in entanglement? Enlighten me, Bob.
Okay, well,
where is it?
Well, you have like two detectors, and they can't even have like a space-like separation between the two. And you have like a joint observation, and they measure it with what they call coincidence counts. And then they have these equations for the coincidence counts. It's funny, you get a very different diagram, or you get like a sine wave with the coincidence counts that's not present when you just take the singles counts at each individual detector. It's the joint one that shows the effect. And that looks to me like something non-local. They all try to say that it involves like giving up on physical realism. And I don't buy into that conclusion, but I think it is something non-local.
Well, I agree with you that in terms of not buying into that conclusion, whether it is actually a demonstration of non-local causality, I mean, how is it that your measurements that you just referred to invoke non-local causality? Aren't there other ways that these measurements could be obtained without that assumption?
Well, you can try a common
detectors
cause, but as far as I know, and there's a literature on this, and you might want to look at it, the common cause hypothesis just doesn't hold up, because everyone tries to come up with that one, and there's arguments. You might look at like some of the things John Bell has to say.
You hit the nail on the head. You brought up Bell.
Yeah.
Okay, I've got a whole paper debunking the Bell theorem or the Bell hypothesis. And it's on my website. And in fact, Bell himself, and I think it's in the very first paragraph of the paper that everybody quotes as establishing what's called as the Bell inequality. Everyone quotes this paper, but the first thing that he says is that everything he's going to say below, this is my paraphrase, now, everything that he says below is in fact dependent on the assumption that we have a non-deterministic system. Well, binary mechanics is deterministic as far as its equations go. And so Bell himself has debunked his own his own hypothesis, and so there we go there. So the last thing you can do is bring up Bell.
Okay,
Bell
but
is
that's
the
an
last thing
issue.
that has any relevance whatsoever to the explanation of so-called non-local causality
Yeah.
in these entanglement.
Yeah, well, I partly agree with you, Jim. I'm not a big fan of like probabilities being basic. But I think you can have a global deterministic system where things are spread out. Uh, so you don't have to
A global deterministic.
deterministic.
What does things are spread out mean here?
They cover a distance, sometimes a large distance. So you have entities that are spread out, like with my shells, for example. I hold that those are spatially spread out over vast distances, even.
Okay, well, thank you, Roger. I appreciate that. Am I right to say that we have sort of a similar view on Bell inequality?
Well, I think the inequalities themselves, as I was saying, the ones that were tested was the CHSH inequality, which is somewhat different from the Bell inequality, but all the tests have come out in accordance with the inequality. So there's empirical evidence for this. It's not just someone's theory.
Okay, can we move down a bit? I'm not really going to touch this one here with quantum fields. Complex amplitudes. Are you dealing with these complex amplitudes and probabilities? You don't really deal with these probability distributions and amplitudes and stuff like that in binary mechanics, right?
No, no. In fact, I look at the complex amplitude as it's used in 20th century quantum mechanics as a starting point for parsing the components of the complex amplitude into parts, which was done in the illustration I've shown above. And so that is more or less just how some of the thought steps that I did to move from the quantum mechanic point of view to the binary mechanic set of postulates and equations.
All right, let's move down. That was a good answer, I think. I'm not, let's keep going. Yeah, now we're do these conditional probabilities and configuration spaces. I think you've pretty much clarified differences there. What I wanted to get to was the 4 points. Yeah, should not be vague. I think we addressed that one. In your case, you have definite equations that are definitive. Everything in binary mechanics is based on an equation, equations that predict what happens at every change in discrete time, right?
Yes.
Okay.
So,
here's the thing, this business of predictions and empirical data agree. This seems to be the big hang up in science, what constitutes a prediction and what constitutes empirical data. That seems to be the kind of the problem with when you're doing a theory and you're trying to convince other people that your theory is correct by this empirical test requirement of a theory. And you're claiming that you've done this in a number of different ways, that you have predictions. But it seems to me that in quantum mechanics, they're doing their predictions statistically, right?
Yeah, the closest you can get to an actual value that is measured is a probability for that measurement, as I understand traditional quantum mechanic thinking.
Right. So what a prediction isn't a prediction of a particular outcome. It's a prediction of a distribution of particular outcomes.
Exactly.
Okay. So what is meant by a prediction is not the same thing in your theory and his theory, I would take it.
Right. No. Like, for example, take the proton positive electric dipole moment. What is that? The electric dipole moment is like the water molecule. It has more positive charge on one side than the other. In other words, it's not perfectly symmetrical. And so therefore you have, it's like a water molecule that has this, what's called electric dipole moment. Now, my work predicts that the proton has a positive EDM. And by the way, if it does, it seems to break some theories in quantum mechanics, which I won't get into now. They're rather technical, but it's, in terms of what they call symmetries. But anyway, the basic overview is that what I do in my work is I look at what mainstream physicists do in well-known laboratories and what the results are and how they may or may not agree with what binary mechanics is saying. For example, the fractional electric charge of the electron was a prediction which now people seem to be accepting. And that prediction was made way back in 2010. The zero electron electric dipole moment shown here was again predicted on the basis of the fact that the negative fractional charges of the electron are distributed equally around their axis of rotation in the electron. So that would give you what, by definition, a zero electrodipole moment. And I think a lab at Harvard, in fact, right there where Jacob is, and one in the UK, both were striving to increase the precision of this measurement of electric dipole moment, or EDM, for the electron. And they're striving to get it more close to zero, to show that in fact it is zero, that their measurements are not significantly different from zero, but to even more significant figures. And so that's what they're competing, as it were, to show that the prediction of binary mechanics is in fact correct.
But wasn't Murray Gell-Mann's hypothesis about the quarks, didn't that predate all these things by quite a bit? I think it was 1969.
Yes, very important. In other words, it's been as Ian correctly said, in my opinion, the recognition of the existence of fractional charge has been around for a long time, maybe more than 50 years or so. And so the new thing is the electron fractional charge. That has not been that has been predicted by binary mechanics back in 2010, but
So
not
that's
recognized.
not part of the original quark theory. That electrons.
Well, no, because electrons are leptons and quarks are quarks. Okay, so that there are two kinds of fermions, electrons and positrons, and then the quarks. So so that no, that was not recognized. As a matter of fact, I think was the first to talk about a fractional electron charge back in 2010.
Okay, because
now,
I thought that was encompassed in Gell-Mann's ideas, fractional electronic charge.
I guess one can read the papers and see what he says about that specifically. I haven't read those specific papers, but as far as I know, no one has claimed, including the authors you just mentioned, Ian, that the electron has a fractional charge.
We got 5 minutes.
They were talking about quarks or quantum chromodynamics, you know, the structure of the protons and the hadrons.
Okay, we got less than 5 minutes. On this point 3, how the classical world emerges, I think the issue there has to do with if the quantum world is non-deterministic, how does determinism in the classical world arise? But you don't really have that problem, it would seem to me.
No, the talk that I gave here on binary mechanics cosmology builds the universe step by step, and I have a plan that hopefully I can get done to transfer the basic contents of that talk to a paper on my website.
Yeah, but it seems to me that if you're saying the quantum world is indeterministic and probabilistic, then you have to explain why the classical world is deterministic. And that seems to be what this third thing deals with. But your theory is completely non-statistical and deterministic to begin with. So you don't have this number 3 problem as I see it.
Correct. That's a good statement. I'll have to quote you, Harry. That's a good way to put it. If you know, like let's look at that. Some people say that our solar system and therefore us on Earth is moving through space at a huge number, hundreds of kilometers per second. And if things were really random, how do we, stay all in one piece? Like as far as I know, an hour or so ago, I had 2 hands that were shaped like this, and wonder of wonders, and after a whole hour of moving at such a velocity through the universe, my hands still have this shape. How could that possibly be if randomness were fundamentally involved? Wouldn't, why doesn't this piece of skin sort of wander off this way? It's random, isn't it? And this piece of skin wander off that way, and then I have a little bone going up and down, and how do I even stay in one piece for the duration of today's talk?
So you're proposing a solution to this conundrum about quantum mechanics, how the classical world emerges from the ideas of quantum mechanics, which are non-deterministic and random.
Yes.
Okay. All right. As for the number 4, you don't have any. You're just saying I have no ad hoc axioms, so I'm good to go. I think that's
right. In other words, I can start with vacuum, which is uniquely defined in binary mechanics. Like, for example, perfect vacuum is just the absence of ions.
All right, we got less than a minute. We need to wrap it up.
Okay. that I can create the universe starting with a few particles and go all the way up to objects like galaxies and souls containing solar systems and so forth. No additional postulates or equations are needed.
All right, I want to thank everybody for coming here and participating. You want to wrap it up in like 30 seconds or so?
Yeah, well, I look forward to Roger posting the video on this, at which point he usually lets us know in an email, and at which point I'm going to give some shine the light on his YouTube channel and that video, and communicate through x.com to Barandes and to his associates at Harvard and so forth, and see how they react. Since
Okay.
okay, bye-bye.